Good morning, good afternoon, and good evening, everyone, and welcome to our webinar titled Untether Your Data with EndoGear, Wireless Volumetric Blood Flow and Pressure Measurement. This webinar has been sponsored by Transonic Systems and is produced in partnership with the American Physiological Society. So a big thank you to them both for helping to make this event possible. Joining us today, we're very fortunate to have Cole McLarty and Dr. Danielle Senador from the Research Division of Transonic to introduce the newest biotelemetry system in the life science field called EndoGear. So without any further delay, I'd like to welcome Cole McLarty to the floor. Cole, take it away whenever you're ready.
Hi, Sarah. Hello, everybody. Thank you for the kind introduction. We're definitely excited to be talking with you today. So I'd like to thank Insight Scientific right off the hop. I'd also like to thank APS and Scientist.com for collaborating with us in this, except what we feel is, of course, an exciting day. I also want to thank everyone who's taking the time to attend. I can see a bunch of familiar faces in the audience, which is certainly very exciting. So my name is Cole McLarty. I'm the Director of Sales and Marketing for Transonic's Research Division. Later in this presentation, I'll be joined by my colleague, Dr. Danielle Senador. She goes by Danny. You'll hear me refer to her as Danny throughout. She's the product manager for EndoGear and also an application expert on our team. So today is actually a pretty big day for Transonic. It might sound a little bit hyperbolic, but this is something that we've been waiting for 40 years. Really, ever since we created this technology, we're going to be talking about throughout the presentation. And ultimately, I think a pretty fair question, given that the life science market already has several very high quality providers for telemetry, such as DSI, which everyone's familiar with, MCA, 80 Instruments, TSE, and many other very quality providers. I guess the first question could understandably be, what value could another provider actually bring to this space? So with all the options that are on the market today, we feel that there's a fundamental measurement that is absent, an essential parameter that is at the center of our company, which is volumetric vascular blood flow. So ultimately, on behalf of the Transonic team, I would like to introduce EndoGear. So EndoGear is the first fully implantable wireless flow and pressure measurement system in the world designed for rodent models. So throughout this presentation, I'm going to give you a review of the features, the components, really anything that you'd ever want to hopefully know about EndoGear, while Danny will also give us an understanding of the applications that we service into, some of the data that it can provide. Ultimately, I think what will be helpful first, just to kind of set the stage, is to kind of give that 100,000-foot view of really what this product is all about. So what you can see is we have the implant body here with appendages coming off of it. And what this equipment offers are really four essential benefits. First and foremost, of course, is volumetric blood flow. We'll be talking about this shortly. Anyone who's familiar with our product will immediately recognize that flow probe. We also have high-fidelity solid-state pressure catheters. We'll be talking about the benefits of solid state technology. We'll also be talking about that really unique design that you see there. Continuous inductive power that allows us to collect data 24/7, which is very important this day and age. As well, we also integrate with all common data acquisition systems. So I will reference what those systems are throughout, but pretty much any system that you might have in your lab will be able to accept signals coming from EndoGear, which is exciting. And then ultimately, of course, a key question that people will have right off the get-go is going to be, what models does this service into? So this equipment right now is designed for models that are roughly about 250 grams and larger, or similarly sized research species. So of course, that would initially be rat. But there's other models, of course, as you scale up from there, that would be acceptable as well. So what we're going to cover today, if we look at a presentation overview, kind of set the stage a little bit further, we're going to first cover the EndoGear flow probes and the pressure catheter that partners with it, EndoGear implants. From there, we'll look at the powering options that we have. We've touched on inductive power, but we'll talk about the full suite, communication infrastructure that goes with it, options for your lab so you can get a better idea of how this could potentially fit into what you're currently doing, application design and data review. This is where Danny's going to come in and really kind of hammer home those really important details that the scientists on this call will be very interested in knowing. And then what we'll do is we'll kind of touch on our support and surgical services, because we don't just simply offer a really interesting technology. We also offer a very detailed background, really 40 years of experience in these specific types of measurements. So if we really jump into what makes this equipment particularly unique and what Danny will elaborate on shortly, as well, frankly, something that I would imagine almost all the attendees already appreciate is that blood flow is an essential physiological parameter. It's a parameter that cannot be accurately interpolated without direct measurement, however. So Transonic is a company that was founded on the understanding that accurate blood flow is a fundamental necessity to understand hemodynamics, cardiac function, pathophysiology, and many other parameters. So in 1983, when Transonic opened for business, the leading technology in the life science space was actually Doppler flow measurement. So Doppler is a technology that, of course, still exists. It's a high-quality technology, but it is a technology that does not provide absolute volume. What it does is it provides a velocity. Yes, if you have cross-sectional area, you can interpret a volume, but it is not providing that without doing additional work. So what we did is we pioneered a technology. Again, this was back in the 80s, and the technology was called transit time ultrasound. So with this, we're able to provide absolute volumetric flow data in various different conditions. So our deployment of transit time is via a paravascular flow probe, which is a flow probe that's placed around the vessel, but does not actually come in contact with said vessel. So it's a non-contact solution. And ultimately, what happens here, as you can see in the photo, transit time ultimately is a relatively simple idea in principle. So what we're going to do is we'll very quickly review through what we have here. So you can see that we have a vessel, we've got a flow probe deployed paravascular, and then what we have is red arrows indicating the direction of flow movement. From there, from the probe head that you can see, you'll see there's two different colored arrows. We're going to look at the blue arrows first. You can see that they're moving from the right direction of the flow probe head over to the left. And what's happening here is we're sending an ultrasonic signal that will transit through as we move from the right to left, it will transmit through the vessel, bounce off that reflector, and then over to the left side of the probe where it will be measured by a receiver. And then at the same time, what we're doing is we're sending a signal in the opposite direction with the blood flow. And ultimately what happens here, again, it's a very simple principle. Our technology monitors the time at which it takes for this signal to transit the lumen, of course, transit time. And what we're able to do from this is derive a very accurate absolute volume. And ultimately, with absolute volume, you can do an awful lot. It's an absolute measurement. You can compare it directly between animals. The thing that's also really important about this technology is that it is established to be rock solid in stability. So stability is a very important principle for chronic data, as we'll kind of see and talk more about. This is one of the things that really differentiates this technology from something like electromagnetic flow. It really just doesn't drift over time, which is pretty remarkable. The other thing that's also very important to keep in mind is that, and again, to be fair, this term, some people will bristle at the term. It is a bit of a marketing term, but it is gold standard. And the reason, I mean, that word is a bit overused, but the reason that we do apply it here is we have 40 years of proven biocompatibility and thousands of publications in this space. Of course, not all of them are in rat models. Many are in mice, larger animals, etc. But we've been doing this. This is our career. This is what we've been doing for the entire time that we've existed here. And a very interesting and subset that we're very proud of is ultimately our long history with chronic tethered success. So part of our library of publications includes the use of flow probes for chronic experiments dating all the way back to the mid-1980s. So we came out in 83. Ultimately, in 85 or 86, we were implanting these things into animals in chronic procedures. So this has always been our plan. That's, again, why this is such an exciting day. These probes are deployed today in many labs throughout the world, including in Dr. Fiona McBride's lab. So Fiona joined us for a webinar recently that you can find in the resources section. You can also find on our website, on Insight Scientific's website as well. And in that, Fiona touches on the successes of this approach, but also, of course, the challenges that come with tethered monitoring. Danny will talk about some of this as well. But ultimately, it is something we've been doing for a very long time, and we've learned a lot from. So taking what we learned from our tethered work, what we did is we designed our new EndoGear flow probes to have some changes. So one of those, if we look at these blue circles here, you'll see that they're ultimately getting smaller. What we've done is we've pretty dramatically reduced the actual cable weight and diameter, and that makes it more appropriate for these specific applications for tunneling the cable, etc. We've also done here is we've taken the flow probe, and we're seeing 3 different orientations, but ultimately it's really the sky's the limit. It's all directed specifically by application, but we can customize these different things to a specific application. And as we move to the probe heads, all of our clients on this call will immediately recognize what you can see here. So this is our very familiar non-constrictive paravascular design that has various flow probe orientation options that are tailored to vessels and measurements of interest. So the probes are available in sizes 1 to 3 millimeters in ID lumen size. So that's the size between the blue and the blue location on the flow probe and ultimately the reflector. And that gives a working vessel range that can go with these probes of somewhere around 0.6, 0.7 to 3 millimeters OD. In terms of actual key applications, what we have here is a vascular tree. And what we're going to do, if you notice closely, some flow probes are going to populate on it as we talk about specific applications. So the first we're going to talk about is what we think could perhaps be the most exciting application, and that would be aortic flow. So we feel that this measurement is perhaps the most scientifically impactful because what this will ultimately do is report stroke volume and heart rate on a beat-by-beat basis throughout the entire length of your experiment. Whether that experiment is 3 days, 3 months, or longer, it will report stroke volume continuously. So for when you have heart rate and you have stroke volume, that gives you ultimately cardiac output. And for contractility assessment, for safety pharmacology, and many other research fields, this will really represent a very important new technology to measure different parameters in that space. As well, for things like stroke models, we have carotid flow for longitudinal measurements. We also have renal blood flow. So this is actually one of our more popular tethered applications. I can see that several people in the audience that I know are actually actively doing this now, literally tethering animals now, which is great to see. And then we also have mesenteric flow. So mesenteric flow was actually featured again in the presentation from Fiona, which again is available for free on demand. And it was actually using 2 flow probes in this tethered application and got some really interesting data. So as we move forward, we're going to kind of move a little bit swiftly. There's a lot of details to cover. We revisit the implant. And what we're going to do now is we're going to look at the middle sensor, which is our pressure sensor. So ultimately, blood pressure is perhaps the most studied hemodynamic parameter in all of science. As alluded to earlier, researchers in our space are fortunate to have a lot of different options when it comes to telemetry needs. And ultimately, pressure is one of the variables that's ubiquitous throughout the industry. So every single provider provides some form of a pressure measurement device, though some providers measure these things in different ways. So of these methods, the accepted gold standard of accuracy and resolution, and has been for decades, is a solid-state high-fidelity catheter. However, the problem with these catheters is ultimately they're very challenging to manufacture due to their extremely small size, sensitive components, and therefore specialized expertise needed to build them. So what we'd like to do is, again, reintroduce the SciSense brand. So ultimately, the SciSense brand has been proud to manufacture solid-state catheters for the past 20 years. As many of you will know on this call, they're actually known for, or I should say we're actually known for, their admittance technology. So this is a technology that allows you to measure pressure volume loops and get volume live without the necessary complicated calibration steps. However, for the past several years, what we've been doing is developing an entirely new catheter from the ground up, one that's designed specifically for the demands of chronic experimentation. So what we have here is a 1.2 French, which is 0.63 millimeters. It is an absolute sensor that is completely new and features a helically wound thermoplastic shaft that really balances flexibility and feedback, which of course is important in any application like this. Like all solid-state catheters, which is again a very important benefit of this technology, there's no signal attenuation over time. As well, what you'll notice, and I referenced earlier, this interesting design. And what this is it's a pressure conditioning enclosure that's actually located roughly halfway up the catheter. So this is actually an important differentiator. It's a feature, not a bug. It is ultimately something that plays 2 important roles. So what it does is it shortens the length of the actual catheter material that's required to be inside the animal. So one of the challenges with some other designs is ultimately you have this very sensitive catheter material that's the entire length of that shaft from the connector all the way up. What this does is it allows for us to break that up and actually have a very flexible white cabling, as you can see highlighted in blue, that can be located at various different lengths like we'll talk about, thus shortening the pressure section just to the amount that you actually need. And then as well, what we did is we incorporated suture holes to also make for stability of that catheter location much more robust. Instead of having to suture down on the catheter itself, for example, you can use these suture locations. which we feel is also very helpful. So as we look about look how this can be customized to different applications. One thing, as you can see highlighted, is the pressure catheter itself. It can, of course, be shortened or lengthened. And if we look at the white cable, again, it can also be shortened or lengthened. So it can really meet whatever the application needs ultimately are. So as we move forward and we look at the implant body itself, the first thing that you'll notice is a pretty dramatic size reduction in what is a very popular piece of equipment. So what you will see here is the implant body next to one of our 400 series flow meters. And so this is, of course, is a flow meter that many of you have in your labs. Located within it on the left-hand side is an SP430 pressure module. It measures pressure from 2 different locations. So the implant on the right really hosts the same type of technology as the flow meter with the actual pressure amplifier in it as well. Of course, there's various different differentiators that make them suitable for their own environments, but the point really is fairly obvious. We actually have reduced the size of this technology by about 370 times, which is pretty impressive, we feel at least. Ultimately, the dimensions now are 30 millimeters by 30 millimeters by 9 millimeters, as you can see in the measurements there. And ultimately, these implants are available with 1 flow and up to 2 SiSense pressure catheters. So in this orientation that has 4 outputs, we'll talk about power shortly, but 3 of those would be taken up, 1 for flow, 2 for pressure, and then 1 ultimately for power, which we will get to shortly. The transmission range of the implant is roughly in the neighborhood of about 5 to 10 meters using RF communication. I use the term roughly, and again, we'll talk very briefly about what that transceiver is and how it works and some of the things that go into really differentiating how far something can actually transmit. So we'll get to that very shortly. And then, of course, included with all of the implant variants is internal temperature to measure the temperature of the animal, and then also activity data via an accelerometer. So, like all implants, ultimately, we require a power source. So there needs to be some way of providing power to this implant. Ultimately, on our side, we have 2 different options. So one of our options is to go with a battery source. That's a 1.2 amp hour battery. And the other is our continuous inductive technology. So given that the value of this data we feel is very high, we also feel and get feedback from our clients that the most suitable for their needs ultimately is continuous monitoring, which partners very well with the inductive power. So less a feature and more of a requirement for this type of technology, though, is for this to be thermally neutral, which fortunately ours is. In terms of layout, our inductive system is composed of 2 parts. The inductive power receiver, which you can see here, which is customizable with, again, that white cabling that you've seen throughout. And ultimately, what happens here is if we assemble this back into a rodent model, we've got our cardiovascular tree, and then we've got our implant inside. What this will allow us to do is actually see the second part of the system, which is our wireless power supply. And so ultimately, our wireless power supply is shown here and partners with the receiver that's in the implant that's attached to the implant and ultimately provides continuous 24-hour data. The base accepts standard rat cages, and animals can ultimately be housed individually or they can be co-housed. And it delivers uniform power throughout the cage. And that includes all of the animal's normal behaviors, including eating, feeding, standing up on its back, paws, etc. So it's uniform power delivery throughout and really allows you to measure continuous flow and pressure data, of course, temperature and activity as well at all times. So what we're going to do now is we're actually going to take this. And now that we have this idea in our minds of what the implant looks like and what the flow sensor looks like and what pressure ultimately looks like, we're going to take a step back and we're going to look at some of the communication infrastructure. And we're going to explain how, as we move away from the animal and focus more on that infrastructure, how things actually plug in together. So we're going to put that to the side. And what I'm going to just simply highlight down here at the bottom is as I step through this section, I'm going to highlight small versions of the components I'm talking about in a daisy chain. That'll really help you connect these together and understand how things work. In the next 2 slides following that, I'm actually going to pursue that even further. So as we jump into things, let's first talk about the transceiver that we touched on briefly before. The remote transceiver is designed to receive data from the implant wirelessly and communicate this data through a wired Ethernet connection with the base station, which is coming up shortly. It transmits data commands to the implant as well as commands coming from different locations within the system, from the base station, for example, that allows you to cycle on and off the implant as well as individual channels on the implant as well. The way this is designed is a 1-to-1 ratio, so each implant requires one transceiver. And ultimately, it's RF communication that is flexible. Flexible simply meaning that you can change frequencies. Ultimately, it houses a barometric pressure offset as well, or a barometric pressure sensor to offset ambient pressure changes. So ultimately, what this is that for pressure technologies, as people will know in the telemetry space, you can have changes in your room pressures that will then affect, of course, the ultimate pressure of the sensor inside the animal because they are that sensitive. So ultimately, barometric pressure can be offset in this manner downstream. And ultimately, this design allows for no disruption to the animal subject. So in circling back to the range, that 5 to 10 meter range, ultimately that simply just is impacted by environmental factors. So anyone who's done this measurement before will know that really depending on your room will really dictate how far these things can transmit. Our suggestion, of course, will be to have it closer to the animal. Next, we're going to talk about the base station. So the base station signals, ultimately it is connected directly to the transceiver, and the transceiver is transmitting data to the base station, which receives that data and also is an interlocutor that transmits commands back to the transceiver so the implant can also be controlled. We'll talk a little bit more in detail about that shortly. Ultimately, this is designed to integrate directly, as I mentioned, through universal BMSc connections with any data acquisition system generally on the market today. And ultimately, not all of the outputs that you see there are required. So in our example, we're looking at pressure and flow. Ultimately, you'd have pressure, flow, activity, temperature, and barometric pressure, which is 5 signals. And those would actually be output in our example. And they would, again, be output to things like Notochord or Ponema or IOX, LabChart, LabScribe, etc. What we'll talk about here now is the multiplexer. So a piece of equipment that is used for sequential data collection. So again, we'll define those items in a moment here in the next slide. Ultimately, this multiplexer is set up for researchers to gather from cohorts of animals, so animals that have all been implanted, data from one animal at a time. So up to 16 different transceivers and therefore 16 different implants can be plugged into one base station, or sorry, one multiplexer at a time. And from there, it intersects. So you can see those plugins at the back. It then will connect to the base station, so a single base station. So 16 of these transceivers can go into a multiplexer that then communicates with a single base station, which then, of course, communicates with the DAQ. One at a time. The eGUI control hub, which is our software system, we'll show you next. Of course, then we'll speak with the multiplexer to control what implants are on or off at any given time. So in talking about the eGUI control hub, ultimately this is located on software. This is provided by us, and it allows for visual management of key implant features such as implant summary tabs, controlling all paired equipment, so on and off, controlling individual implant channels. So if you had a battery, for example, and you wanted to turn off a power hungry type of data, but wanted to leave on something that was less power hungry, you can actually do that. It houses implant ID and settings files, global tools to test implant functionality, and it's also customizable scheduling. That's actually where this happens. The automated scheduling of implant cycling in sequential data collection modes is housed here. So just given the fact that we're introducing you to this new technology, we understand we're giving you an awful lot of data pretty quickly. So hopefully these next 2 slides will really hammer home exactly how this is all integrated together. So if we take a step back and we want to look at a couple like very specific examples, I think it's probably helpful to just simply define some of our terms. So simultaneous, as we see highlighted here, simply means exactly as it sounds. We're going to be measuring data from all animals at the same time, 24/7. Sequential, of course, is when we're managing from a cohort of animals, all with an implant, but data only one animal at a time. So in this example, we have 3 animals equipped with a wireless inductive power receiver, so they're inside of their base, and we have one transceiver per animal. So we have there is one base station per animal, and as you can see, that's bidirectional communication. From there, we have those base stations plugged into the eGUI, which is controlling the implant through the transceiver and the base station. And ultimately, those base stations are then feeding to a data acquisition system, which then feeds to your computer. So ultimately, what this really essentially means, you can see how this scales, is in this layout, you need one base station per implant and one transceiver per implant. That then will dictate your data acquisition needs. And ultimately, what we can see here is that this data is being transmitted to all animals or from all animals at the same time. As we move over to sequential monitoring, we look at the same cohort of animals. Again, 3 is just something we picked at random. Ultimately, what happens here is these 3 transceivers will plug into one multiplexer. And again, we can measure all the way up to 16. In this example, we're simply looking at 3. And it's bidirectional communication as well. That then plugs into a single base station. And that single base station then interacts with the data acquisition system in a computer as normal. But the key variable that we again want to highlight is in this scenario, what happens is you're measuring from one animal at a time, as you can see from our bars that are moving around. So this is definitely something that people need to assess whether or not this is suitable for their needs. For things where you're looking to suss out circadian rhythms or very specific data sets, this may not be the most suitable, and that's where continuous data might come in. But ultimately, the good news is that you have options. So with that, what we're going to do is we're going to start talking about a couple different variables, and I would like to introduce Dr. Danielle Senador to walk us through that. Danny, I pass things over to you.
Thank you, Cole. Thank you for the introduction. Well, now that Cole has presented the EndoGear platform and the telemetry implant for pressure and flow, I would like to give an overview of what can be done with the product. Let's start with a simple recap of the pressure and flow relationship. As Cole mentioned, I'm just giving an overview. Dr. Fiona McBride has presented a webinar recently where she explained this concept in depth and also some aspects of blood flow regulation in vivo. So please make sure to check the resources section on our website, Transonic's website, or Insight Scientific's website if you have missed it. So going back to this formula, as we know, resistance can be calculated as pressure divided by flow. The role of blood flow itself is to deliver nutrients and oxygen at an adequate rate between delivery and consumption of any given tissue or organ. But how does this adequate rate happen? First of all, we have to remember the following. One, different vascular beds supply different organs and tissues. Each one of those have individual requirements. These requirements can and are indeed different according also to circumstances. And lastly, circumstances can range for simple events such as standing up or more complex ones such as disease states. So how do all this come to play? How is blood flow modulated? Multiple systems and multiple systemic and local mechanisms work in unison to attend to the blood flow demand, ultimately via vascular resistance and pressure. In addition, each one of these mechanisms have interdependencies with opposite and redundant subsystems, resulting in a balance towards less or more flow according to the tissue-specific demand. The clear message here is that this is a complex and important hemodynamic variable to be evaluated and always must be evaluated in context. So, as a company that is dedicated to flow measurements, we have actively participated in countless studies over decades, enabling blood flow measurements in many in vivo models. Our legacy, of course, is based on tethered setups, but we all understand the importance of untethering the flow data. As we know, any untethered system highly facilitates the ability to collect data 24/7. In theory, continuous data collection can be accomplished with tethered systems, but the data is more susceptible to issues due to animal manipulation and or hardware connection mishaps. The need to let the animal acclimate after being connected to the recording apparatus or swivels getting disconnected mid-experiment. These are all very common challenges in the lab. So, of course, the advantages of telemetry are well known. So since today we are presenting our telemetry system for pressure and flow, let's look over some data from one of our recent studies done with our EndoGear implant. This specific study was designed to verify known circadian rhythms in flow, pressure, and other variables. Why did we decide to look at circadian rhythms? First of all, those are discrete but well-known patterns that are highly susceptible to stress, even at low levels. So, a study that shows the preservation of circadian rhythms in animals implanted with EndoGear would signify the following. 1. The system is indeed able to capture discrete oscillations in flow, pressure, temperature, and activity, which are the implant outputs. 2, we can confidently correlate these oscillations with known circadian patterns. Therefore, we are able to discard the hypothesis that these fluctuations are random system artifacts. And 3, we can also reason that the chronic implantation itself produces minimum stress. So let's take a look at the study details. First of all, I would like to say thank you to our academic partner for this collaborative effort. So the study, 4 animals, Sprague-Dawley rats with body weights ranging from around 380 grams were instrumented with EndoGear implants. The implant configuration had 1 flow probe, 1 pressure sensor, and a wireless power receiver, as we use inductive power in the setup. On the next image, showing a ventral view of the implanted animal, we can see where each component of the device was located. The flow probe was placed around the ascending aorta. This was achieved via a right thoracotomy on the 4th intercostal space. The pressure sensor was placed in the abdominal aorta. The surgical approach was via a midline laparotomy of the lower abdominal area. The entry point of the pressure catheter was the left iliac artery, and the catheter tip containing the sensor window was then advanced into the abdominal aorta up to just below the bifurcation of the left renal artery. The implant itself was positioned in the abdominal cavity, and the wireless power receiver was placed in an abdominal subcutaneous blockage in the same abdominal area. Here, in this lateral view, we can see how the wireless power receiver is positioned more superficially than the implant. The rats were monitored for 6 to 7 weeks with no post-op complications or any complications throughout the study. I would like to take a moment here and share a few important details of the post-op care and observations. These animals were mobile after anesthesia effects were completely gone. Food and water intake were normal within 24 hours post-op. And also, these animals received only non-opioid low-dose pain management for 3 days immediately after surgery, with no need to adjust the drug regimen at any time. So now let's take a look at the data. To start, this slide has a snapshot of the data from one animal for illustration purposes only. The top panels show the blood wave, specifically cardiac output, as the flow probe was placed around the ascending aorta. The units are millimeters of blood per minute. The lower panels show the arterial pressure wave in millimeters of mercury. Flow and pressure waves on the left were collected during the light phase, while the data on the right were collected during the dark phase. In this snapshot of the flow data, we have a good example of how peak flows were higher during the dark phase. The scale is the same in both flow graphs, and the top dotted lines are here to illustrate the differences in peak flow. As expected, part of the architecture of the wave from the ascending aorta hovers at 0 with every cardiac cycle. Here, of course, unchanging healthy animals, regardless of the time of day. When we look at pressure, we can also see higher values during the dark phase. However, for pressure, the whole wave shifts, as dotted lines again help illustrate both systolic and diastolic increases. Circling back, these are just snapshots for illustrations purposes, to illustrate, observe circadian differences and how waves look on display. The circadian analysis was conducted on data recorded continuously for multiple weeks. So let's take a look at that data now. This data analysis was performed on a 10-day segment of the total data collection. In the slide, we have mean arterial pressure, mean cardiac output, calculated from the ascending aorta flow wave, heart rate that was also calculated from the aortic flow wave, total peripheral resistance, also as a calculated measurement, which is mean arterial pressure divided by cardiac output, temperature, and activity. Each data point in the graph represents 4 rats data average in every 1 hour interval, plus or minus the standard error. In every graph, the vertical dotted lines delimitate each day, while the gray backgrounds help identify the dark phase periods in each day. When we look at all the parameters, with the exception of resistance, which we will address shortly, we can see the expected circadian pattern characterized by increases in the variable during the dark phase. Parameters increases are emphasized here with the red trace over the dark phases shown on gray background for better visualization. Going back to the resistance graph, when we think of circadian cycles and the associated higher activity of certain physiological systems, especially for blood pressure, heart rate, and to a degree sympathetic activity as well, it would be logical to initially think that total peripheral resistance could be higher or even unchanged during the active phase. This is not the case. The active phase is marked by a decrease in total resistance. This is not new data. The mention here is to draw attention to a twofold example of the relevance of continuous flow and pressure monitoring, as it illustrates how this specific pattern could go undetected without continuous longitudinal data, and also to show the complexity of the cardiovascular system, showing a prevalence of vasodilatory mechanisms over several vasoconstrictive indicators. I would like to add here that we'll be presenting this data and many other details of this study at Experimental Biology. If you would like to know more, please stop by the Transonic booth or come by our poster. And lastly, before I conclude my portion of this presentation today, I would like to make a few last comments. This protocol with cardiac output and mean arterial pressure has been replicated multiple times with a larger N, and also with academic and industry partners. The implantation period average for all these studies has been around 4 to 5 months, with some studies exceeding the 8 months mark. The protocol replication with different collaborators has time again relied on our surgical support legacy, doing training and setup with different teams in different facilities, always with extremely positive outcome, with our long term of history of working closely with our customers, helping developing surgical protocols for chronic flow measurements in many different vascular beds. We are excited with the opportunity to use this expertise now on the telemetry platform. Thank you, and now back to Cole.
Thanks, Danny. Appreciate that. So obviously at this stage, we're about to wrap up. You can see that with any telemetry system, there's certainly a lot of variables, and certainly there's going to be questions that you'll have. We're looking forward to getting those questions. Even then, there might be questions that might go beyond questions you might have tomorrow. And that's really where our support, surgical services, and some of the ways in which you can contact us, I think, become particularly valuable. So ultimately, as Danny touched on, application development and training is paramount with any telemetry system, but particularly one that is going to introduce a new measurement, at least a new measurement perhaps to you. And so the key thing we want to identify is that we have a team of application experts. Danny is a member of that team, a leader in that team, but one of several, actually. And so each of our application experts have a PhD in their respective fields and years of experience in chronic instrumentation and also, of course, surgical expertise. So with that in mind, we really want to make clear that really when you start becoming interested in this product, hopefully, we're able to really help you from the beginning of application development all the way through to actually executing on your specific protocol telemetrically. And a big part of that is going to be the 40 years of flow measurement expertise that we can bring to bear. So every application that you would want to do with a paravascular flow probe, we have done before. It has been published. We have an application note for it, etc. And we can bring that expertise that is all relevant, same probe head design, all completely relevant to this telemetry space. And it really puts us in a pretty good position to really help you. And partnered with that, of course, is on and off-site surgical support for all EndoGear users. I think the important thing to highlight there is all. So our intended structure here is to provide on-site surgical training for all new users without exception. And this will really help, we believe, in making sure that you're using the technology really to its utmost potential, and also making sure that the process going from being a new beginner to hopefully publishing will be as smooth as possible. We also have ongoing and evolving support materials. So that includes surgical videos and application notes. And as you can, of course, expect, we're introducing this technology, and there'll be new support materials that will be generated as new applications come on board. But that really, again, circles back to our application team who will be working on these types of materials. And of course, we'll be doing future webinars on those topics. The other thing that's ancillary and really connected with our application team is our larger team in general, and that also includes sales reps. We're very fortunate at Transonic to have a very dedicated, experienced, and skilled team. And what I mean by that specifically is a team that has been doing this, frankly, for years. We don't have any junior members on our team. I think the youngest individual on our team has been with the company for 5 years, all the way up to, I believe, all the way up to 30 years with the company. So we really do know this space very well. We know the people that play in the space. We understand how to use the technologies, and we're really interested in being value added to you should you be interested in working with this equipment. We'd also like to introduce the concept of EndoGear in industry. So academic needs and industry needs will potentially be slightly different, and industry in particular could be interested in 2 services that we provide, which is surgical implantation services, as well as data analysis services, which is something that you can certainly inquire with us during the question and answer period or after this presentation as well. So as we wrap things up, we want to discuss some opportunities to connect with us. So as Danny mentioned, we're going to be at Experimental Biology, which is April 2nd to 5th in Philadelphia. So please come see us. We're going to have an EndoGear booth at booth 419. As well, Danny also referenced her poster. So the title for that poster is Continuous Ultrasonic Transit Time Blood Flow and Arterial Blood Pressure Monitoring in Freely Moving Sprague Dolly Rats via Implantable Telemetry. So it's quite the mouthful. It's probably the reason why she didn't reference the exact title during her presentation. It wouldn't have fit in as a title. Ultimately, our new EndoGear webpage is also available. This is really where you're going to go if you're left with questions that you'd like to perhaps see if you can answer yourself. If you want to learn more about the product, you want to get the full brochure, the specific data sheets that will talk about power requirements, specific sizes, volume, sampling rates, all those different pieces of information will be located there. Abstracts, blogs, webinars, both past and future ones. And ultimately, we're really looking forward to providing more EndoGear content and other Transonic content coming soon, such as our new Advantage ADV 550 pressure volume equipment that will also be launching at Experimental Biology April 2nd to 5th. So there's an awful lot going on that we're very excited about. So with that in mind, I'd like to wrap things up. I'm going to pass things back to Sarah, and we really look forward to hearing from you guys in the audience and see what questions you might have. Thank you.
So I'm going to start the Q&A with our first question.
Great.
So this question says, I am currently measuring tethered cardiac output with your equipment. What are the surgical differences in tunneling with EndoGear in regards to the flow probe?
Danny, do you want to take that one?
Yeah, I'll take this one. It's a very interesting question. Of course, the basis of this technology is our body of work with tunnel and tether systems setups. So usually the tunneling for flow probes or any or pressure sensors in rats is through the scapular area. And that also, I must add, that comes with handling exit sites for the length of your protocol. It's something that's tricky, that people have used it know very well, that issue. And also the connection of a tether system. You need to be watching the connection as you are recording the data. The interesting thing that I want to bring attention about the implant and the way it's configured, for an example, the flow probe, every sensor of the implant, it's hardwired. So you're going to have to tunnel the flow probe from the general position that you anticipate your implant it's going to be. If you recall from the presentation from one of my the middle slides showing the rat with the implant is in the abdominal cavity, and then the flow probe goes to the chest. So we tunnel from the abdominal area through the thoracotomy area for the implant position around the ascending aorta.
Fantastic. Great. Thanks for that. The next question here, and actually many people have had this, so I'll summarize. Is the EndoGear implant reusable, and can it be refurbished?
Danny, that'd probably be a question for you as well.
Yes, it is reusable. It is designed to be reusable. One thing that's interesting, of course, partner with the inductive power, it extends the life of the implant, for how long you can keep those implants. You're not constrained by batteries. So as far as the reusability, it's like any device that needs to be explanted to be placed again in another animal. It's going to be a question of how well that equipment is going to survive the explant procedure. For as far as refurbishment, we don't have refurbishment for this system.
Right. Yeah. And so just to kind of maybe expand a little bit on that, the question of reusability is also very common with solid state high fidelity catheters in general. So we get this question with our pressure volume system. We get this question with our pressure catheters, which of course are all designed to be reusable. However, the amount of use that you can get out of them really is directly proportional to how they're treated, which again circles back to some of that support stuff where we're obviously very keen on making sure you understand how to explant appropriately, which will then give you success in the future. So just wanted to add that in. It's definitely a variable that is hard to pin down because there is some onus on the user themselves in using these types of technologies. But that's obviously why we're here to help, so you can get the most out of the technology for sure.
Definitely. Okay, I'm going to move on to another question here. So this is about animal model use. 2 questions, so I'm going to again summarize. This person says, I'm working with mice. Will EndoGear be offered for mice? And someone else has asked, what about large animals like pigs?
Okay, I'll take that one, Danny. So yeah, this is an expected question for sure. Just the classic saying, of course, you come out with something new and somebody, of course, says that sounds great. What else can I do with it? And so if we take a step back and we certainly look at what applications we can service into from an animal model perspective, mouse is certainly a goal. Being candid, it's not our first priority. Actually, our first priority is, of course, launching the equipment in its current layout, but also I think what you'll see in the coming months from us, actually relatively quite soon, will be some news on the large animal side that we're very certainly excited about. And check back with us, certainly, of course, moving forward for mouse applications. I will say from a tethered perspective, absolutely. This is something, again, that we've been doing for decades, measuring flow in mouse models, certainly. But again, the miniaturization of the technology needs to get to that level. So, yeah, we're working towards it, but it won't be available, say, in the next 12 months, not for mice.
Great. Another similar type question of this is great, but what else can I do with it? Are there other sensor types like ECG or blood oxygen available?
Right. Yes. So again, an expected question. There's lots of different applications that people want to service into. Pressure and flow partnered together, of course, is what we feel highly valuable. I think a lot of people agree with that. But ECG is certainly something that people have already commented on and our collaborators would like to see. So what I can tell you is yes, from an ECG perspective, that is absolutely something that we're looking to onboard. Blood oxygen, nerve stimulation, various other types of interesting applications are on the potential list for sure. I think really what we're looking forward to doing is really getting feedback from the field on what applications would be most of value, frankly. So the easy answer is yes, ECG. Things like oxygen and other things are on the question mark list. We'd love to hear from people. If there's a list of things that people would like to see from the equipment, we're absolutely listening.
Great. Okay. The next question here is, I think, directed at you, Danny. This question is asking, the data that you presented was mostly focused on the cardiovascular system. Can this system be used in stroke models measuring carotid flow?
Well, absolutely. One caveat, of course, that would be great is, again, expanding what the product can do and speaking to what Cole just said, like we want to know what people want to do with the equipment. Yes, for the stroke models, I just want to add a few considerations here. I think this product would be phenomenal for interrogating longitudinally carotid blood flow in models that we know for a fact that are either induced by manipulation of carotid flow and or that have an outcome that you can detect or you expect to detect oscillations in carotid blood flow, for an example, atherosclerosis, new models that are coming up. There are many different models of stroke. So definitely I can see the product being able to help some of those protocols for sure.
Fantastic. Okay. This next question is, if using the inductive power system, can the animal or animals be taken out of the base to record data?
Right. Okay. Danny,
Cool.
it's okay if I take that one?
Please.
I'll take your silence as a yes. So what we're referencing here would be, if you guys remember back to the previous slide where we're talking about you'd implant an animal, that animal would have a wireless power receiver that's connected to the implant. And it's communicating, of course, wirelessly, or not communicating, it's receiving power from the base station. And the question really circles around, is there any power provided to the animal when they're outside of that cage? Really, the question becomes, is there a battery on the inside that provides power? And the answer is no. So this is a technology that's designed to provide power within the cage, 24/7 from any location within the cage, as mentioned, co-housing, all those nice things, but no, it will not provide power outside the cage. And that's really where the battery comes in. For shorter term protocols or for these exercise physiology models or behavioral science or anything that you'd want to see the animal outside of the cage, that's really where a battery model would be most suitable at this current time.
Okay, great. This is tying into an earlier question asking about mice, but this person has asked, has anyone worked with this technology with animals that are smaller than 250 grams?
Danny, I think you've got some experience with that, if I'm correct?
Yeah, I'll take this one.
Okay, great.
With the different studies that we've done, as I said, we work with different partners, different facilities, of course, a wide range of animal weight. I think we pushed the envelope there a little bit, and we had success with animals around 220 grams. That I think was the lowest that actually were part of the group of animals, and there was no different outcome than the rest of the animals at 250 and higher.
Okay, great. We definitely have time for a couple more questions here. So great. This person is asking about, I have not measured flow before with your technology. I'm thinking they're meaning tethered. Is that going to be a problem?
I'll jump in on that one, Danny. So the short answer is absolutely not. That's not a problem at all. The reason that we reflect back on that, again, circles kind of back to our history. Flow measurement, of course, as you guys have seen, is certainly what we do. But we also have a really strong history of onboarding people, or at least what we call it in the sales division, onboarding someone to be successful in these measurements. And that's really where the application experts come in. So I guess it circles back to the final slides and really talking about training resources. So the short answer really is no, it's not a problem at all. It's actually going to be probably the most common thing that we're going to see in this space. And that's really why we feel that on-site training is so important. Perhaps it's maybe an odd approach. I know other providers will say that on-site training is optional. Of course, in reality, it's optional from us as well, but we will strongly suggest it because we feel that it will give you the ability to really benefit from the experience that we have in these measurement systems. People will simply have questions about how to optimize a flow probe in a specific application related to tunneling, or where should the implant be housed if I want to do something different, like spinal cord research, or various other applications. And fortunately, we have a lot of experience in all of those different places. So the idea here would simply be, if you haven't measured flow before, that's not a problem at all. What we would do is simply circle back to our application design phase, which, Danny, of course, if you want to jump in and expand on that, you certainly can. But really what this means is we would support you in getting up to speed on that measurement specifically, in partnership with also getting up to speed on EndoGear more broadly. So we definitely have a program in mind for that.
Yes.
Absolutely.
Yes, and it's a program like with the data that we discussed was just one of the studies that we conducted. I presented the data here today, but we of course did different ones. And I want to say most of these partners didn't have the experience with flow, and we used our model of providing this kind of support for Tether. Now is the difference that it's for EndoGear. So we were able to put in practice also this model for specifically for the EndoGear platform with a very high success rate. And it's been a learning process and a very constructive process as well. So it's been very engaging to help people that have never done this kind of measurement, writing the first surgery and get the signals. It's definitely huge milestones, and it's exciting.
Yeah, perfect. Okay, I'm going to ask the last question here because we're almost at the top of the hour. This person has asked, does the development of connective tissue between the vessel and the probe affect the Doppler signal? So this is for the flow probe.
Danny, actually, I think I'll jump in on that one. And the reason I'll jump in on it is, so my background is so I'm the director of sales and marketing, but I've been a sales rep previously for 10, 11, 12 years, somewhere in that zone. And this is one of the more common questions. And frankly, when I started at the company, it was something that I didn't fully understand. It seems almost counterintuitive. But fibrosis and connective tissue is actually our friend in this application with this technology. So ultrasound in an acute application really requires a coupling agent. So it requires something to get rid of air. Ultrasound doesn't like air. In a chronic environment, that is less of a variable, actually, because ultimately what ends up happening is you have connective tissue that will grow in relatively short order, typically within a period of a day or two. And what will happen is your signals can actually... Sorry, go ahead, Danny.
Yes, I'm just agreeing.
Oh, right. Okay. Yeah. And so, again, I guess the reason I wanted to jump in, Danny, of course, you can add some background to this as well if you think it's necessary. But the real answer here is no, actually. It's not a problem at all. And ultimately, it ends up becoming a real benefit to the measurement itself. It still allows for vessel growth, of course. And that's where that non-constrictive design is so valuable, where it allows for vessel growth, and this connective tissue along the way is also helping with signal transmission. So somewhat counterintuitively, no, it's actually not a problem at all. And it's something that's working really in tandem with our technology, which is a nice benefit, I suppose, for us.
I just want to add something here. Mm-hmm. Can I add something? Just the last bonus of the connective tissue is that it also further stabilizes, mechanically stabilizes the flow probe around the vessel. So,
great.
Good point.
Awesome. Well, I want to take a moment to thank you both. We really appreciate your insights and for sharing this new tech with us. And it was a pleasure to have you on board today.